Alright, how's everyone doing today?
Good.
Good?
Alright.
Awesome.
Midterm's coming up.
Midterm is coming up very shortly. So I posted a not particularly specially ordered list of things to study or possible topics for the midterm. So we can go through these and talk about it, but if you have any questions now or during or after, just ask. So I've written your midterm. It's going to be 6 questions. So roughly 20 points each. One is like 15, one is 10, or however that adds up. Yeah, 2 15s and 3 20s. So not planning any surprises. Same drill that you've had on the other 224, 222 exams, right? Basically writing some code, analyzing code, modifying code. I don't have short answer or multiple choice questions on this one. Some of the questions may only take a few lines to answer, so don't feel like, even though I gave you a full page with lots of blank lines on it, don't feel like you need to fill in every single page. Just do what you need to do to answer the questions. Okay, there aren't really a whole lot of tricks on here. So if you think, well, that's only going to take 6 lines of code, write your 6 lines of code and move on. Okay, a couple of the questions will definitely take a lot of code. Well, not a lot of code, but you know, they're full-blown programs. But some of it is going to be pretty straightforward. Most of it's going to be straightforward, I hope. So don't make it harder on yourself than it's asking. If you're not sure, you know, how much I'm asking for, you can always ask for details. So 6 questions, 15 minutes, 4 double-sided pages of notes as usual. So all the same drill. All right, so just some things that came to mind that you should think about in preparing for this. So obviously make sure you're comfortable with classes and objects. Okay, classes are the recipe, objects are the things you make with the recipe. Okay, classes are like the blueprint for the building. The buildings are the actual objects. They're the things constructed. You know, they're instances of the class. So how to define a class: class name, curly bracket, blah blah blah, closing curly bracket. And mostly there's fields and methods inside a class. So fields are variables, right? And if you define a field outside of any functions, any methods, it's a class. It's a variable for the whole class, right? So you can access it from any method inside the class. And it's kind of like a global almost, right? In that it's accessible from everywhere throughout the class. If you define variables inside methods, then they're local to that method. Okay, so kind of the same as C. So methods are just functions, fields are variables. And the other thing you find in classes are constructors, and those are things that tell you how to create the object. So they do initialization mostly. Methods take an optional keyword like public, private, and then a type of return variable, the name of the method, and then a list of variables in the argument list. Constructors are the same, but they don't specify a return type. So public, my class, parentheses, whatever arguments would be a constructor for my class. Public, private basically control who has access to the fields or methods of a class. So if it's private, you can only access these things from inside the class. So a private method can be called from other things inside that same class. It can't be accessed from outside. If it's public, outside code can reference this object, construct object, reference this class, construct objects from it, and then run the methods or access the fields. And then getters and setters, accessors and mutators. So generally, if you have variables that are listed as private, you don't have the ability to touch those from outside the class. If you want to give someone the ability, you can create a setter where you can say set variable, and they can call a method. The method has to be public, and that method will have access to this private field. And you can use accessors or getters to read that value. Again, you can write a method, and the method will have access to it, even if it's private. And if that method's public, then an outside class can use that method. But why do you want to use a setter and getter instead of just making these things public?
Information encapsulation.
Yeah, so this is information hiding and encapsulation. Basically, you know, if you're making a stack class, you don't want somebody to monkey around with a stack pointer, right? You know what to do with the stack pointer. If somebody decides they want to just clear out the stack and they just come in and say set the stack pointer to 0, well, maybe you wanted to do something like overwrite the contents of the stack whenever you decrease the stack pointer, and they've just short-circuited that piece of your mechanism, right? So you protect the stack pointer, you say that's private, and chances are you would never even give the person an opportunity to see the stack pointer, because they just want to say push pop is empty is full. So it lets you control how much information the outside world has access to. Okay, so be prepared to write code, analyze code, modify code. Linked lists. So you did linked lists of linked lists in PA2. I will not ask you to do a linked list of linked lists, but I will ask you to do something with plain old linked lists. So if you're reviewing PA2, I would say take a look at your location list, because that's a linked list of integers. Take a look at your word list, because that's a linked list of strings, but don't worry about the location list part of it, right? But word list was a good example of inserting things in order, searching for things in the list. Location list was a good example of traversing a list and just inserting at the end. So basic concepts of linked list. Linked lists should be implemented with a different type of object for the nodes, right? You can have a class called linked list. You should probably have a class called linked list nodes, and your linked list is a linked list of those nodes, right? And if you made it work by just having one type of object, right, make sure you know how to do it with a separate type of node also, because that's more like what you're going to see. With or without sentinels. Okay, so we're working without sentinels in this course, but you know, sentinels are still a good thing to know, but make sure you know how linked lists work without a sentinel, which is basically if the list is empty, you have a null in place of a list of nodes. And so your code has to deal with that. You can't just start at the first node and see if next is null. You got to see if the first node itself is null, right? So that changes a bit of the edge cases. And then how to do things with a list, how to add a first node, how to add other nodes, how to add nodes in order, how to traverse the list and see everything that's in there, how to search for something in the list, delete from the list, and so on. If you wanted a list of strings, you should be able to do that, or a list of rectangles, or if you want a doubly linked list where you have a previous as well as a next pointer, you should be able to cobble that together. Just add another field to your node class and do whatever you have to do when you change the list. So know everything about linked lists. You'll be safe. Specific classes to be comfortable with, and make sure you understand the scanner class. Okay, how to construct a scanner object, which if we do it from system.in, that's a way to set up a scanner to read standard in. You can also construct from new file parentheses file name, and that will set up a scanner to read from a file. That's got to go inside a try-catch block, because when you construct a scanner from it, if the file doesn't exist, it will give you an exception. And I mentioned try-catch later on. And then the main things we do with a scanner, next line, next int, next double, etc. Right? There's all these methods that basically say, give me the next something. Okay, so plain old next says, give me the next token. And tokens by default are things separated by some sort of space. End of line, new line, a space, a tab, form feed, whatever, right? Plain old spaces. So next gets you a word at a time. Next line gets you an entire line at a time, so everything up to the end of line character. Next int gets you the next integer, and so on and so forth. And then associated with each of those, there's a has method, so has next line, has next int. and so on, which basically tells you if there's another one of these things ready to read. So those usually go together. We usually while loop around, has next, for example, and then use next inside the loop. So brush off your code for that, write some test code if you're not comfortable with it. And you can expect to use scanners in some of the code you write on Wednesday. String class, you should definitely know how to work with the method's length. So length tells you how many characters are in the string. Character at lets you reference an individual character. So string.charat0 gives you the first character of a string. String.charat2 gives you the third character of the string. And strings in Java are not arrays of characters. Okay, they're strings. We think of them abstractly as just a collection of characters. But we can't say string bracket 2 to get the third character like we do in C. So if we want the nth character, we use the charat method, charat n. 2 uppercase, 2 lowercase, return an uppercase or lowercase version of the string. Things that aren't letters aren't changed. Things that are letters get changed to uppercase or lowercase. Substring we haven't really used, but it lets you pull off a piece of a string. So you can say substring 0, 5, and it'll give you all the elements of the string from character 0 through character 5 minus 1. So the first 5 characters. Compare to, you've definitely worked with. That's like string comp. So it compares its argument with the current string, tells you which one comes before or after the other. And it returns an integer whose sign tells you how those two strings compare. Dot equals tells you if two strings contain the same characters and the same length in the same order. And you should know why dot equals is different from using just equal equal. Right? Equal equal, S1 equal equal S2 says, are these the same object? S1 dot equals parentheses S2 says, do these two strings have the same set of characters? And that's usually what we want to know. All right, you should know about the toString method. So toString is a way to typically take an object and return some sort of reasonable representation of it. But toString can really do anything that you want. So it's a public method. It returns a string, takes no arguments. But the use of it is that if you try to concatenate an object to a string, the system will call that object's toString method. And whatever string it returns, that's what it'll concatenate. And so most commonly this is used when you're trying to print information about an object. If you just say print line and there's an object, it'll turn it into a string using the toString method. So usually, if it's a rectangle you want to print out, you want to return a string that tells you something that says this is a rectangle, this is its dimensions, and so on. But it can be anything that you want, right? You could write a toString method that deletes some file in the current directory. That would be a really pathological kind of toString, but Java doesn't care, right? It's just going to call this and it's going to take whatever string it returns and use that as the value of the object in the concatenation. So generally toString does not print anything, doesn't do anything weird, right? It just returns a string that somehow captures the essence of the object. And if you don't write a toString, there's still a toString available, because objects have a default toString and everything is an extension of object. We'll get to extensions in a minute too. So there's always a toString, but if you write your own, it overrides the default. All right, signatures. So in C, the name of a function uniquely identifies the function. In Java, it's a combination of the name of a method plus the types of arguments it expects. So cool method that takes an integer is different from cool method that takes 2 integers, is different from cool method that takes an int and a double, different from one that takes a double followed by an int. 4 totally different methods, different signatures. So the signature is the combination of the name and the types of arguments. And when you make a call to a method, the JVM looks at the name, looks at the types of arguments, and then tries to find something that matches that signature. And if it does, that's the method it'll call. And constructors have methods also. Same thing, name plus types of arguments. All right, try catch. Basically, if you have a piece of code that's potentially going to throw an exception, you can put it inside a try block. So know how to write try catch blocks. Okay, know the syntax for exception, etc. If something fails in the try block, you jump down to the catch block. When you reach the end of the catch block, you just continue on. If the try block succeeds, the catch block is skipped completely. And if there's a finally block, it gets executed after either the try or catch block finishes. And there's the funny behavior with returns with respect to finally blocks, which is in the quiz. So one of the quizzes that's been posted that was due today, I didn't actually have listed in the modules on the main homepage for Canvas. So I put that in there and I extended it until tomorrow morning, so it's got an extra day. So if you didn't know there was a quiz and you didn't get an email on it or something, it should be on the main module page. And I'll make some more quizzes after the midterm. All right, arrays. So a few details about arrays. So this is the declaration of an integer array. This says x is going to be an array of integers, but this is like saying integer star x. You're not ready to use this array yet. If you try to use it, you'll get an exception. So if you say integer star x, at some point you have to say x equals malloc 10 times size of int in order to make space for it. So to use x, you have to say x equals new int and then bracket however many integers you want. Now x is ready to go. You can talk about x0, x bracket 2, x bracket 9. And if you want to know the length of the array, you can look at x.length, no parentheses. It's not a method, it's just a field. And in this case, that would return 10. All right, that's all there is to it if you're making an array of primitives, things like ints or doubles or booleans, lowercase. If you're working with objects, there's an extra step you need to keep in mind. So let's say we want an array of rectangles. Alright, so first line declares R to be an array of rectangles, second line constructs that array. So now there's 10 pointers, 10 references to rectangles. If I try to call, say, the area method on R bracket 1, I will get a null pointer exception.
Because nothing has been inserted.
Because nothing has been inserted, right? So this is an array of 10 references to rectangles, but each of those references is null. So before I can use, say, R bracket 1, I have to construct a rectangle. Maybe I give it arguments, whatever the constructor is. And then I can use that object. So it's kind of a double step that we have to do for arrays of objects. First we have to use the new keyword to actually create the array, but we also need to use new to create each of the objects. All right, statics. Static methods and fields versus instant methods and fields. Right, R is an instance of rect. Rect is the name of the class. R is an object. It's an instance of a rectangle. And assuming you construct it at some point, right? If I say r.area, it's accessing this method as part of this instance. Okay, so this is an instance method. It's the plain old method we've been working with for the last 6 weeks. The different one is a static or a class method. If we were to do something like rect dot and call some method. Right, this is not an instance of a rectangle, this is the class rectangle. This is a class method, which is also called a static method. So static methods are accessed as part of the class itself. Instance methods are accessed as part of an instance of the class, an object. And the same with fields. So classic examples of statics, math.py. Right, that's a field associated with this class itself. Or math.square-root. And if you want to define something to be static, you just throw the keyword static in the declaration. Otherwise, it's assumed to be an instance method or field. All right, so class extensions, right? We can have a class I can make a class called mine, and I can say it extends some other class. Let's say it's called base class. Okay, so if I say call some method or assign a value to some field or whatever, those are things inside the class that I'm currently inside of, just as usual. Okay? If this method is not actually written somewhere in the description of the class, right, it will look for it inside this base class. So the effect is that this class mine, as soon as I say extends base class, it inherits all the methods, all the fields from base class. But if I write my own version of one of those methods or to declare my own version of one of those fields, it will override what was in the base class. And if I make such an override, but I still want to get to the thing that was in the base class, that's where I can use the keyword super. So super.method would look for method inside that base class. Plain old method will look for something inside the class mine. And if it doesn't find it in there, then it'll look for it in the base class. And this has mainly come up in dealing with the paint method inside the graphics class. And I'm not going to put graphics, swing, window builder, or paint on the midterm. So don't have to stress over those. But they'll be on the final for sure. So any questions, concerns, thoughts? I'd say look over your programming assignments, look over your code for those, make sure it makes sense, maybe try rewriting pieces of it without notes. Obviously look at the notes you've taken for this class, specifically around these areas, and you should be fine. Yeah?
So are we allowed notes for this meeting?
4 pages double-sided, 8 pages single-sided. 2 pages double, 4 pages single. You can probably expect the morning class to be pretty packed, but I don't know that for sure. But that seemed to be where a lot of people have signed up, but probably about 15% of the class is not coming to class, so there's going to be an influx somewhere. I'm guessing it's going to be morning, but I don't know for sure. So. And both exams should be comparable in difficulty. All right, good. So we had started talking about exceptions on Friday, or multi-threaded programming on Friday. But here's what I realized. So Wednesday is the midterm. Thursday is open lab. Friday we'll probably go over the midterm and we'll talk about PA3, which means, or PA4, which means everything that I wanted to talk about for PA4 has to happen in the next 25 minutes or tomorrow. So we're going to push aside multi-threaded programming for a week or so. And I want to talk about trees, because you'll have to use trees in PA4. And implementing trees in Java is a little bit different from how it was in C. It's actually more fun, but it can feel a little quirky at first, because we've done it so much in C. So let's take a look at how we would implement a tree. And you're going to need to write your own tree classes for PA4. I don't want you using pre-built ones. So let's think about trees. So let's make a class. I'll call it my tree. And just like with linked lists, we're going to have a class for the tree itself. We're going to have a separate class for the nodes of the tree.
For the left and right node.
Yeah, so each of these nodes is going to have a left and a right and a data. So let me make a separate class over here. And let's just call it T node. That's the individual nodes. And we'll keep picking on trees of integers. It'll be more interesting in PA4. But let's just say integer data. And then we need a left and a right subtree, and what kind of object should left and right be?
T nodes.
T nodes. So that's potentially all there is to a T node. So what about a my tree? What's the one thing that every tree has that we use to kind of like do anything else with the tree?
It has some kind of sentinel or a pointer.
Yeah, what do we call that? It rhymes with boot. Root. Excellent. And root's going to be a T node. And if your tree is empty, just like with a linked list, root's going to be null. And that's probably the only piece of information we need for a tree is just the root, because that gets you to everything else, right? So let's think about methods. So to create an empty tree, all we've got to do is construct an object of type myTree. And since root is set to null in the declaration of root, constructor doesn't really need to do anything. So we don't even necessarily need to write a constructor for this. So let's think about our main program. Let's see what we want to do with these.
We want to add to the tree.
We definitely want to add to the tree, so we might do something like this. My tree, I don't know, I'll call it MT for my tree, equals new my tree. And then we might say mt.add 20, mt.add 10, and mt.add 300, because I always do 30. And we would hope that at this point the root of the tree was pointing to a 20, which came down to a 10, and over here came down to a 300. And then we might want to do some kind of traversal. But traversal is fine if you happen to know that you want to print the string to standard out. But a more useful thing would be to have some kind of toString. So we might want if we could just take an empty string and concatenate MT, right, the name of my tree, we would hope that that would give us maybe, you know, a list of nodes separated by spaces in left node, right traversal order. Or we could do mt.toString if we don't like concatenating. but we would hope this would give us something like 10, 20, 300. And we might do something like if mt.contains and give it some value, and that should tell us whether or not the tree contains that value. And maybe a delete method for deleting, but deleting is kind of ugly, right? So we're not going to worry about that for now. PA4, you don't need to delete from your tree. So we can probably live without spinning out a delete algorithm. But certainly we want to be able to construct, add things, and somehow look at the contents of the tree, possibly with a toString method. All right, so let's think about an add method. And I just said mt.add. It doesn't return anything, so this is probably a public void add, and it takes an integer n. I'm going to mix this up with some pseudocode, so even if it looks like Java, it's probably not. Well, what was our add algorithm like in 222? What's the human description of how we add to a tree? Thinking recursively, okay, because we want to do as little work as possible. So how do we recursively add a node to a tree?
Give it the root.
Give it the root and do what?
Check its data.
Okay.
Depending on its data, you either give it, tell it to traverse, tell it to look at left node or right node.
Okay, exactly. So to add n to the tree, we basically see if n is bigger than or less than the root. If it's less than, then we want to add to the root's left subtree. If it's bigger than, then we want to add to the root's right subtree. Okay, we have to do one thing before we can do any of that code if we don't want to get an exception, though.
Check to see if the root is null.
Check to see if the root is null. I'm hoping I never have to write that again for any of you, because I've written that a bunch of times. So I think you've got it. So see if root is null. So if the root is null, what do we do? How do we add a node to an empty tree?
Root equals node.
Yeah, we create a new node and we set the root equal to that. So if root is null, root equals new t node. And let's assume we have a t node constructor that takes an integer n and gives us back a node. Set the root equal to that, we're done. Just return. So our t node class needs a public t node integer n, data equals n, left and right are null. All right, so that's a pretty easy case. If there's nothing in the tree, if the tree is completely empty, root's null, just make a new node, set root equal to that, we're finished. Okay, otherwise, we want to compare the data to root's data. So compare n to root's data. And suppose n is less than root's data. Then what do we want to do? So if n is less than root data,
Tell it to add to the left subtree.
okay. We want to add it to the left subtree, which is root.left. There's a complication here, though. The add method that we're writing right now is part of the myTree class. root.data, we're going to add to root.left. Root.left is a t-node. So we're trying to write the add method in my tree, but we're going to need to call the add method for a t-node.
So you have an int and a t-node.
Say again?
You have an int and a t-node in your declaration for add.
Oh, I could pass a t-node to it, but that's going to make things weird down the road. Because if we want to think in terms of objects, the way we're thinking is object.method. Right? So what I'd really like to do is something like if n is less than root.data, then I'd like to do root.left.add n. But that means we're going to need an add method inside t-node as well. And this is the part that feels a little quirky sometimes. But what's going to happen is this add method is really just a wrapper around the add method inside the node class. Because we're going to recurse by starting with a node and saying call add on the left, call add on the right, and so on. And since left and right are t-node, we got to have an add inside here. Okay, so if the root is null, we just make a new node and we're done. Otherwise, if n is smaller than the root data, call the add method in the left child. But this is potentially going to give us an exception if root.left is null. Then root.left.add is going to throw a null pointer exception. So we kind of need to say if root.left is not null, then go ahead and do this, otherwise do something. But that's making a bit of a mess. So let's not do any of this. Let's think recursively, let's think lazy. If nodes have an add method, which say add to the tree rooted at this node, here's all you got to do. Just say root.add. So my tree's add method is two statements. If the root's null, set root equal to a new t-node and return. Otherwise, call root's add method to add n. So it's really just a wrapper around the t-node's add method, but it also checks to make sure that root exists. And if it doesn't, if this is the first node you're adding in the tree, we got to do something special. All right, so inside the t node, how do we add a node? Well, this is 222 now. So we know that the node we're in can't be null, right? It exists because we're running a method inside that node. So we simply have to say, should we be inserting to the left or the right? So if n is less than data, we want to insert it to the left. Well, here we got to say, well, if there's a node to the left, we'll just call that thing's add method and be done. So if left is not null, then just call left add n and return. Otherwise, left equals new t node n and return. So if n is smaller than the current node's data, we want to insert on the left. If left is not null, just call left's add method. If left is null, make a new t node, set left equal to that, and you're done. And then same thing on the right. And there's your whole add. And this is the structure we're going to have for all the code that we write for trees. When we do search, if we want to do search recursively, again, my tree is going to have a search method that's going to call the root node search method. And the root node search method will say if data equals n, return true. If n is less than data, return left dot search n. And if data is bigger than, if n is bigger than data, return right dot search n. Right? And if left is null, then return false. If right is null, return false. So does this look doable, manageable?
So instead of creating the programs inside our tree class, we're creating it inside the node itself.
The actual stuff that does the actual work is going to be inside the node class. But these can all be private. And the public add method is part of the tree class. Because in main, we want to create a tree called MT, we want to say mt.add. We don't want to say mt.root.add, because then we got to have the root be public, and we'd like the root to be private. So the only way they can get to stuff in here is through an add method, or a toString, or a search, or a delete, or whatever. All right, should we try this? So there's our empty tree node. So if root's null, we have an empty tree. So the empty case gets taken care of there. So there's an add method. So there's a T node. There's left and right. There's a constructor, it takes an integer, makes a single node with the same data value, left and right are null, so this node has no children. Here's our recursive add method. All right, so decide whether to add to the left or the right. So if left is null, If left is null, just make a new node and stick it on the left. Alright, otherwise if left is not null, just use its add method. And then do the same thing on the right. Make sense?
What happens if we add to the tree and the node already exists?
Yeah, we're kind of brushing that under the rug here again. So we're assuming that your data doesn't already exist. If it does, it looks like this will go ahead and add it to the right. And I think it will do horrifying things.
Yes.
Yeah, I've never actually tried this when the data's already in there. What does it do? So if we try to insert a 300, it'll go to the right. It'll try to insert 300. Well, that one will work, but that's okay. What if we try to insert 20? So it'll go to the right, and then it'll say go to the left. Oh, it'll come. Does the right thing. Yeah, so it stays in order. You just end up with multiple copies of your number, but it should still be in order traversal, right? Because it'll come down here. It's like inserting 20.00001.
That's slightly unfortunate.
It looks really quirky, but that's actually a perfectly valid way to store 10, 20, 20, 300 in a binary search tree. That's good. I'll sleep better tonight. All right, if I talk for 50 seconds, I don't have to compile this in front of you. Because I don't know if it'll actually compile. What the heck? Oh, yeah, I can't make that private. I should have just left it protected. All right, there we go. Hey, no seg faults. We're good. All right, that's a good place to end. So think about traversal, and we'll do traversal tomorrow. Traversal is really fun when you write this as a two-string. It's like...
Traversal sounds really simple.
Yeah, it's even simpler than simple when it comes down to it. So we'll play with that, and we'll look at some of the other operations on lists. All right, so I'll see you tomorrow.